others are coming. The last time, yesterday we left off with this, the Nernst equation. This calculates the cell voltage in somewhat water non-standard conditions. This equation here, because it has the 0.0592 volts, is only valid at 25 degrees C. So, but that's normally what we use for all our calculations is 25 degrees C. So we'll go ahead and write it here. So E of the cell is going to equal E of the cell under standard conditions minus 0.0592 volts over Z or N log base 10 of Q. And so this example here, we're going to have a cell under non-standard conditions. And so if we look at, we have a platinum anode. And at the platinum anode, we're going to have iron 2 goes to iron 3. So this goes reactant product anode. At the cathode, this will be reactant product at the cathode. And so we can take that cell diagram and then just draw up a schematic of this cell here. And that is at the anode, we're going to have a piece of platinum. And what we're going to have here is the iron 2.
I wasn't able to print out tomorrow.
Yeah, tomorrow. So we have iron 2 going to iron 3 here, and that's going to give up one electron. And that one electron is going to be fed over to the cathode. At the cathode, we have our oxidizer, and the oxidizer here is just going to be silver ions. So the silver ions are going to pull that electron to deposit silver metal here. Coming through here. And then we'll need some salt bridge. Under standard conditions, all the concentrations would be 1 molar. So we have 1 molar iron 3 plus 1 molar iron 2, 1 molar silver ion. And that's kind of weird because usually you don't want a lot of product in there. We're trying to make a product. So if you already are starting off with 1 molar, then it's kind of waste in that case. But we have to do it to be under standard conditions. This is going to be under non-standard conditions, although the cathode is under standard conditions because this is 1 molar. The anode is not 0.1 and 0.2 molar. And so here we have extra product. The reactant's at 0.1, the product's at 0.2. That's going to lower what we have at the anode is oxidation. So this is going to lower the oxidation potential, having more product there. And so this is going to be a 0.2 molar, and this is a 0.1 molar. This is at 1 molar. And so, first off, let's go ahead and calculate it if we were at for under standard conditions. So we need to calculate E naught of the cell. E naught of the cell is assuming everything's at 1 molar. That's going to equal the anode potential plus the cathode potential. The anode potential is, oxidation occurs at the anode, so this would be the oxidation potential. Reduction occurs at the cathode, so this would be the reduction potential. If we look at what the oxidation potential is, it's the oxidation potential for oxidizing iron 2. Now, we don't use a bar here because they're the same phase, being oxidized to iron 3. So I'm going to separate it with a comma here, plus the reduction potential. The reduction potential is reducing silver ions to silver metal. Now I use a bar here because these are separate phases. And so comma for the same phase equals a bar here for different phases. So I go to my table. The table is the table of reduction potentials, but the oxidation potential is just the reverse. So let's first look up the oxidation potential for iron 2 goes to iron 3. Okay, here it is. So we have iron 2 goes to iron 3. Now the forward direction is reduction, and that would be the reduction potential. So the reduction potential is plus 0.771 volts. The reverse direction is going to be oxidation. So we're oxidizing iron 2 to iron 3. If we reverse this, then we change the sign on this. So it's negative 0.771 volts. Okay, then we look at the potential for silver ions going to silver metal. It's here. Silver ions going to silver metal is 0.800 volts. So we'll just use that as is because that's the reaction law. Plus 0.800 volts. And so this will be 0.029 volts. So E naught of the cell is 0.029 volts. Now, Z is the number of moles of electrons transferred in the balanced chemical reaction. And so we have the reactant for the anode and the product. Iron 2 goes to iron 3 plus 1 electron. And then over here at the cathode, we have silver ions plus an electron goes to silver metal. And so it's 1 mole of electrons transferred. So Z is 1. Now Q is going to be the products over the reactants. So let's go ahead and calculate what Q is. Q is equal to the products. And different ways we can see that. We can see that in the combined reaction, probably the easiest, or we can see it here. One way we can see it is based on this. This is reactant to product. So iron 3 is a product, reactant product, silver metal is a product. So this is a pure solid. Pure solid's activity is 1, so it's just iron 3 concentration and divided by the reactants. The reactants would be iron 2 and silver ion concentration. Or we could see it over here. Iron 2 plus silver ion goes to iron 3 plus silver metal. And so this is going to equal the concentration of iron 3 plus divided by the concentration of iron 2 plus and the concentration of silver plus. And then solid silver is metal. Well, we have the concentrations for this. Concentration of iron 3 plus is 0.20. Iron 2 plus is at 0.10. And silver is at 1.0. So this is just going to be 0.2 over 0.1 is just 2. It's log of Q. Log of 2. So let's calculate this potential here. So we'll take the log of Q, which is log of 2 equals times 0.0592. And then we'll take the and subtract it from 0.029. And so the voltage has gone down to 0.0179 volts. And so we'll just call that 0.011 volts. So under standard conditions, we would 0.029 volts, but now we have more product built up here. 0.011 volts.
So the Z was the number of electrons?
Yeah, moles of electrons transferred in the balance. And so you see here is where you see Z is.
Right.
In this case, it's this one. Okay. Okay.